So, we're off on our schedule just slightly as far as our coverage. Today we're going to actually be covering the templates from C++, and then we'll get into inheritance polymorphism either later this week or starting next week. Your assignment this week is to take that linked list that you finished right before the break, or you're almost finished with from right before the break, and convert it into a template. And by the time we're done with today's discussion, I think the idea and concept of a template should be better. So you'll know what we're talking about there. Welcome back from the break. Here, we're going to start actually by looking at a little bit of Python code. So this code has a function named smallest, which just compares two items, finds out which one's the smallest according to the less than operator, and returns it. If B is smaller, or if it's the same size, B gets returned. But if they're the same size, we don't care which one gets returned, right? Just straightforward. Okay. Down here, I've got a little bit of code to exercise this smallest function. I first compare two integers, then I compare two floats, and then I compare two strings using the smallest function. Let me just demonstrate then. When I run that, the smallest item shows up, right? If we go back and look at our test data, we had 2 compared to 3, 2.71 compared to 3.14, and hello compared to goodbye. In each case, the less than operator correctly selects the right smallest item, right? Go back to our sample data there.
So why is goodbye smaller?
The G comes before H. They're sorted alphabetically. Strings are sorted alphabetically. And in reality, what's going on there is it's sorted, you know how string compare works that we used earlier in this semester, where it compares ASCII codes? The less than operator that operates on two strings in Python actually just uses the string comparator. Okay, any other questions about this? Other than why? Okay, so let's look at some similar code now. On the right-hand side here, we have a function named smallest written in C++. The trick with C++ is C++ is strongly typed. When you declare a variable, you have to say what type it is, so the compiler knows before your program ever runs what kind of data is going to be stored in there. And that's necessary so that things such as the less than operator knows how to work on that data. Right? Because integers and doubles and strings are all compared differently. Python is dynamically typed. Not strongly typed, but dynamically typed. The interpreter figures out at runtime what types are stored in the variables A and B, and then looks up and finds the correct comparison operator at that time, at runtime. So Python runs slower because it has this dynamic typing going on, this figuring things out at runtime that the C++ compiler figures out at compile time. So this code's faster, but this code's simpler. I have one function over here. I'd have to write 3 functions if I wanted to be able to compare integers, doubles, and strings. Not only that, if I wanted to compare 2 students, I'd have to write another function. If I wanted to, anything I want to compare, I have to write another function if it's a new set of type, right? And yet, this code is the same. The only difference is in my signature of my function. Point taken? Okay. Now, your first instinct might be, ooh, can you even do that? I've got 3 functions called smallest that all take 2 parameters. It's actually okay. C++ is just fine with that. It's called overloading. let me show you. Over here, this is the code that calls those functions over there. The C++ compiler now, when it looks at this call to the function smallest, sees those two values being passed in, recognizes that those are integer types, so it goes and looks for a function named smallest that takes two integer parameters. As such, it finds this version of the smallest function and invokes it, or sets up the call for it. Here, when smallest is called, m and n are both doubles, and so the compiler looks for a function named smallest that takes two parameters, both of which are doubles, and then eventually will find this function and make sure that function gets called, and likewise for the string version. So the compiler is actually operating based off of the type right here. Not just the name, but it cares about the types as well. So overloading is just fine. The compiler arranges for the correct thing to happen. Now I got to show you one more piece of code here. And that's that piece right there. So in order for this, I actually separated out this file here. I've got the main file. Can't see the name, can you? My main program is over here, which is doing all the calling. This is the function that actually has all the function definitions in it. It's in a separate file. So in order for both the function implementation file and the file that actually invokes those functions to get along and make sure they agree on the definitions of these functions, we actually create a header file here where we put the signatures for our functions in there. Notice that my functions all up here don't have curly braces after them. They're not function definitions, they're function declarations. They're saying that we will have functions with these names sometime by the time the link phase occurs. Remember preprocessor, compile, link in order to actually create an executable? Should I redraw the picture? Okay. Having no yeses, I assume everybody just agreed with it. Okay. So, the one thing that's probably new for you is this keyword extern. Is that new?
That's new.
Okay. Extern just lets this code over here know that this is externally defined. It's in some other object file somewhere else. Don't look for the actual code. It's somewhere else. Okay. And it's good form for you to put that in when you have a header file that's declaring functions for a library like this. I consider this to be a mini library. Okay? All right, any questions about this basic code here? Got one no. Two no's? All right. So I'll assume that everybody's okay with this code. All right. Does this seem like a waste of effort to have three different functions that do the same thing?
Yeah.
And it feels like a waste, right? In fact, anytime you copy and paste, you consider it to be potentially a bad move, right? And I copied and pasted and replaced the types as I created these three different functions. I wrote the first one, and I copied and pasted and did a search and replace to create the other two versions. That's usually a sign of either a weakness in the language you're using or a weakness in the way you're using the language available to you. We don't like to do copy and paste. We like modularity. We like code reuse. So we try not to do that. Okay, first let me go to another file here. This one file right here actually replaces both of the header file and the CPP file that implemented smallest before. This introduces the C++ template. Template is a new keyword. Get it highlighted correctly for you. And it basically says that we need the compiler to be more flexible in its type system. We need it to dynamically figure out the type of values. When I say dynamically, what I mean is the compiler still figures out the types involved, but the compiler figures it out at compile time as opposed to you, the programmer, figuring it out at programming time. So these are the different times when decisions need to be made about your code. And what we're doing is we're pushing off the decision about how we compare two objects to the compiler rather than us worrying about it. Remember, Python actually pushes it clear off to the runtime. Okay, so the syntax up here, that's basically the same. I took one of those functions that said smallest, and all I've done is replace where it said int or double or standard string and replaced it with t inside the function definition here, right? In addition to that, I had to put this phrase up at the top before my function that says that the function that's about to come is a template for a function. It's not an actual function, it's a template for a function that I want to be created. And that function has this function template has one type in it. And that type is then specified inside those angle brackets. I say class T to indicate that T is a type, and even though it doesn't have to be a class, like int and double are not classes, right? But I still say class T to indicate that T is a type, and anywhere in this function definition that this T appears is a place that when the template is instantiated and a function is actually created by the compiler, a type needs to go in there. So the way that this works the code for main looks the same. The only difference here is it's including that file rather than including the other header file that had the externs in it. So at the point that the compiler sees this function call, smallest int, that's what it sees. It looks through the functions that it's seen declared. That includes anything that's been declared inside of a header file that it's included, as well as functions that have already been declared in this particular source file. And it looks for a function with this name that takes these two types. Now, in this case, it doesn't find one, but it does find a template for a function named smallest that takes two parameters of the same type. So the compiler then, at compile time, takes this set of code, those 5 lines, and makes a copy of it and compiles it with t being replaced by int. Compiles that up and stores that in the object code for this module. As we proceed along, the compiler comes here, finds this function called to smallest, which takes 2 doubles. And so it looks through all the functions that it's seen already, and it hasn't seen one called smallest with 2 doubles, but it has the template. So it instantiates another version of the smallest function, this time with t replaced with double. And so it's figuring it out at compile time based on the types of these parameters. Now, if I had another column here that called smallest with 2 ints or with 2 doubles, it wouldn't instantiate the function again. It would realize it had already used the template to create the function and use the version already created. Finally, it runs into, this version has 2 strings, and it instantiates it again with t being replaced by std string. And then the compiler is done with this module, the linker goes and links it up, and because this particular file, this tmain.cpp, was compiled and with that header file included and those template functions instantiated, the object code for those are in the object file with this. And so it's all ready to link up. Yeah.
So, going back to where we'd be doing our linked list, how would we be able to handle a constructor where we have more than one type?
So this is function only so far, right? We haven't looked at the class version of template just yet. But the trick is that with your constructor, first off, your constructor would look like this, right, if you were templated off of T, because the constructor is named after the class. Inside here, you'd be, actually, I take that back. Constructor goes something like this. Whatever the name of your class that's containing other things. Your parameter here, if you were doing an initialization, sending in a student object or something like that, or an arbitrary object, might look something like that, where you're using this T from the template. Then, inside, when you initialize, the data member within your object, from this object being passed in, this data member would have this type as well, right? Now, whether that's int or student or particle or whatever it is, player, whatever the class type is, if the assignment operator is correctly overloaded for that particular type, then the assignment just works and the compiler makes sure the correct assignment operator is called when it's templated. I answered the question I thought you asked.
No, that's right, yeah.
So, it's time for rebuttal or re asking.
Well, I guess the only other question would be when you're going to be dealing with 2 different types.
So you have 2 different types within the same template?
Right.
Let's say I want to compare type 1 with type 2 in my smallest function. Then my template up here would say template angle bracket class T comma class U close angle bracket. And then I use T where I want it and I use U where I want it.
Okay.
So that list right there is a comma separated list. Even though we have angle brackets, I still call those parameters, they're template parameters as opposed to function parameters. But it has similar syntax to the parameter list that you use for a function. So
can you override a template, like if you wanted it to handle a certain type differently?
So if you had one type that needed to be handled one way and another type that needed to be handled another way, then you'd probably use a combination of overloading and templating. So you would overload it for the special case and template it for the generic case. And the compiler, again, would be looking based off of the declarations it's seen. So as long as you have the header declaration for the special case before the template declaration, it will pick it up. If it's not defined, then the overloaded one will take place. So this is just a quick demo that, given the same input data, all three versions do the same thing. I wanted to point out that the only reason I put these names on them, there's nothing special about the T or the CPP or anything here in the file names. Those are just to separate the code within my same source tree that's doing comparisons between different ways of doing the same thing. Okay, so that's templates for functions. It's important that you realize that templates always go in header files and not CPP files. Okay, my first version where I used overloading, I had smallest CPP and main CPP. I'm shortening their names, but those are the two source files that I had. I had smallest.h, which was included by both of those, right? So the reason to do that, include it in both places, to make sure that both functions agree and on the actual signature of your functions. The compiler will catch if you, for example, define smallest here, the smallest function here one way, and declare it here a different way, the compiler will complain and you'll actually end up with an error, or at least a warning, if not an error, run compile time, so you'll know you made a mistake in your consistency. Okay, so when this compiles, main.o ends up with a single function defined inside of it. It's got the source code for, not the source code, the object code for main. Meanwhile, smallest, when it's compiled, ends up with three versions of smallest. So all of those have object code that are in this object file. Then, during the link phase, we end up with our main function then that pulls this function's object code and all three of those functions' object codes together to create the executable program. All of it's tied together, right? Okay. Now in the template version, main CPP includes smallest h. Main.o now actually ends up with all of the code implemented in it. I'm going to abbreviate string right there. So it ends up with all four of those functions, object codes here, and at link time, the main executable is created, and all of this is all that's needed. Now, we could instead have tried to do this with the template version. Okay, in this version, smallest.h would only have a declaration that there is a template for smallest. It wouldn't actually have the implementation. By implementation, I mean the entire 5 lines. You could put template like this and put a semicolon right there to say there is a template like that, and then put this implementation into the CPP file. So there's a problem with that. That means that smallest would be compiled to smallest.o, and main would be compiled to main.o. Well, the issue there is main.o would have the object code for main, and then it would have a reference to these other 3 templated versions. It would be a reference to them that they must exist, and at link time they must be added in, because that's where that would be tied up. Because if the implementation isn't there, then main.cpp can't compile it into main.o, right? The compiler just can't add it in. Okay, we have an additional problem though, because in smallest.cpp, we include smallest.h, and then we have the template that we have up there. But the compiler, if it doesn't see a call to the templated function, it doesn't actually instantiate a version to handle that. So unless you call smallest with 2 ints, call smallest with 2 doubles, call smallest with 2 strings, those versions won't be compiled into smallest.o. And so the version that we would have nothing in it. Which means at link time, the linker would try to create our executable, and it would have main's object code available, but it would know it needs these, but it wouldn't have them anywhere, and so you'd actually have an undefined symbols or undefined functions at link time as you try to link that program. So for templates, this version doesn't work. Non-templates, that's the correct way to do it. But for templates, you put all your templated code into a header file and include it. The compiler then compiles it down at compile time. Instantiates the correct version based on the template. Does that seem okay? Now, in your linked list assignment, you probably have a structure that looks like this. You probably have main, student, and list CPP files. You then have your list.h and your student.h. Main probably includes both of those. List probably includes both of those, while student only includes that one. Probably. Then, when you compile these different classes, or these different CPP files, you end up with main.o, which has only the main function and any other functions you wrote to do your testing, right? Read the file in, populate your list, and things like that. Student.cpp ends up with student.o when it's compiled, and it has all of the student methods in it. And finally, list gets compiled into list.o, and it has all of your list methods in it. Now, inside of here, there are references. Write references in here. If I have one. You have references to student methods inside of here. Here you have references to student methods and to list methods based on the actual calls you have, right? So that when you link all 3 of these together into your main executable, you end up with a complete executable and no undefined, because all of the references to student methods inside of main.o are resolved against the student.o file. All the references against list methods are resolved against list.o. List.o again has all of its student references resolved against the student.o. And the linker is able to produce for you a single executable that has all of your code in it. That's all good, right? Some of you actually put your student and list classes in the same files. But this is an expanded version of a more modular way to write it. But if you only have 2 files instead of 3, this is still the same principle. The references back and forth are there. The header files make sure we have the correct references, and then the CPP files have the implementations. Okay, we are going to look at a templated class. Let's say that the list were not a normal list, but it was a templated list. It's a container that contains stuff, and you want that to be a template. Well, you would change your structure over here then. You would not put all of the list implementations in the list CPP. Instead, you put them in the list.h. So you would instead have main.cpp, which would include list.h, and it would also include student.h. You would still have student.cpp, which would include student.h. Those would get compiled down to object code, and those would get linked together into an executable. But this main.o then would house not only the code for main, but also all of the implementation of a list that stores a student. All those methods that apply to a list of students would be included in this object file. So that's the structure of your assignment this week. Let's do a little bit more of an example then. Okay, so if I'm in Python and I want to make a class to contain something, I'm going to call it box because I have no originality. So spell correctly. Okay. Sorry, I didn't have that written for class. That's a very, very basic container. It contains a single item, right? Using the dynamically typed nature of Python, the box doesn't care if we're taking ints or floats or strings. It just stores whatever we send to it, right? As long as whatever we store can be assigned correctly and can be returned and can be assigned again, that's all we need. The dynamically typed nature of Python makes that work for us, right? Okay, so let's go to the C++ version of that. So if I say class box, hopefully, probably need protected or private. Private. And I want to store an int. I would say int data, and then I would have box int data in, and I don't need a destructor because I'm not using dynamic memory. I say int get data. Void set data data in. Right, there would be my header file. And my CPP file then would say include header file, and then I need all of my methods implemented. Right? And no questions? It is Monday, I come on break. I don't see any rock stars sitting out there. Talk about the beverage, not your programming abilities. Okay, so that works for storing an int in this container, right? In this simple container. What if I want to store a double? What if I want to store a string? What would I have to do?
Write those over again with double and string.
Okay? Write them all over again with double and string as the type. Wherever int shows up, then I need to put double or I need to put string. It's even worse than that. With the function overloading, my smallest function, I could just do that, right? Just rewrite them and the overloading would work. With my box class, it doesn't work that way. I can't just call my new class box. I have to call one of them box int and one of them box double and another one box string. Or I have to give them different names even, right? So it would be actually a real hassle for me to be able to do that. Whereas I want some code to be able to be written generically that can do the same thing that this main function right here can do. I want hopefully I get this right really quick. I want to be able to create a box that stores an int, a box that stores a double, a box that stores a string, I'll worry about this code in a minute. But I want something to work like that, right? So that when I create the object, or when I create the box, it will actually be able to be initialized correctly. The intention is correct, is understood? One set of code that does all of this. Well, I actually have to make one modification to this code first. First off, I have to say this box stores an int, this box stores a double, and this box stores a string. So, as a programmer, I still have to tell the compiler a little bit of a hint when I want to use a templated class. Then the code that we have there will work. So I'm going to need to include my templated box header file, which we haven't created yet, in order for this to work. Don't forget my IO string. Still haven't dealt with that. Okay. So I want my templated version of my box. I'm going to go right here. And start with that. Now, in order to template it, I have to say template, class, and then I use T most of the time for my first template type, just because I started that way, so it's a convention for me, kind of like when I do a loop, I use I, but it's not required. I usually use uppercase in order to signify that it's a type, make it stand out more, because I use lowercase for variables most of the time in my code. Okay, then down inside my code, I basically then just have to replace everywhere there's an int that I meant to be this arbitrary type that we're storing, I replace it with T. Now, if I had a list where I was storing ints in my list, and I had some int that was keeping track of how many items were stored in my list, then the int that's tracking the number of items would not be my templated type, it'd still be an int, right? So only replace those things that make sense, that are part of the type that you're trying to replace automatically. Okay, well that gets me started to say that there is this class called box, which is a template, but in order to complete the code, I need to write all the methods as well. And the methods are now template functions, just like previous template functions we've seen. And since they're templated, they have to go in the header file here, not in the CPP file. So I've collapsed the box CPP and the box.h into the box t.h so that it's a templated version here. Sorry, that was a lot of me just pounding on the keyboard with belt link. Questions?
One question I've been wondering is with the nm def at the very top, do we have to have the CPP defined in the front like that? Because I remember us doing it just name of the file and the H.
That symbol could be anything you want. I name mine after the file that it's in, so that if I uniquely name my files, then the symbols are also uniquely defined.
Okay.
And I have, just for this source code that I'm doing as an example, because I have many different versions of it, I'm pre-pending the CPP underbar as part of my file name.
Okay, so that's
just for me to keep my source code organized. So no, the CPP is not required. The H at the end of that symbol isn't required either, but it follows the H of the name.
Yeah.
Okay? Cool. Other questions? Okay, so since the main file is including that header file, I should be able to compile this up if I get things taken care of real quick here. Okay, so let me show you the compiler error that I was getting and then explain it to you if you'd like to know, so when you see it, you'll know how to fix it. So this compiler error that I'm seeing right here is line 16 of my file. It's right on this line right here. It says invalid use of template name box without an argument list. So the compiler knows that box is a template. It sees this word box right here and doesn't see this after it, and so the compiler says that's an error. You basically have to, whenever you're talking about the box type, you have to put the template parameter after it. So in a sense, that's like trying to invoke a function that's expecting parameters without giving the parameters. We're trying to invoke a template without giving the template parameters. Now it compiles just fine. So that was my error there. So if I run that file, that program now, you see that I get my before message, the 1, the 3.1, the hello come back out just fine from these outputs. So I'm able to store those different types. Now you might have noticed in the Python version then, I played a little bit of trickery here, and I actually set data types into those classes that weren't the original data types. So B, which was originally storing an int, I put a string into. C was originally storing a float, and I put a float into it. And D was originally storing a string, and I put an integer into it. And in Python, that wasn't a problem, right? Because Python doesn't care. It's dynamically typed. Well, even though we're playing with templates, C++ it still cares. It's still strongly typed. So when I take this B object, which stores integers in it, it's a box of ints, and I try to put a string into it, then I'll get an error message about trying to put a string into an int spot. So I can't do that anymore. It's still not ultra flexible like dynamic typing provides. If I do put the correct types in, it compiles and it'll run okay with the modified versions coming out afterwards. Okay, that was a whirlwind of a quick demo of templates not only as functions, but also as classes. The biggest use for template classes is for containers, like your list. So you can make a list that has all the list functionality, but not have to rewrite it every time you want to store something else in a list. You can write that list code once as a good template, and if it's efficient, works well, and then you get the errors out of it, you can store anything you want in it, as long as the data type you're storing has the correct operator overloading done. This is kind of where we're leading up to with C++. This is how we're going to be flexible and dynamic, write code once and use it a lot, is by using things like templates and overloading. Okay? This is where we're headed. We're going to find out later in a couple of weeks that somebody did most of these templates for us already too. So you get to write them, but
this is like math where we do the really, really, really long way, and then they're like, by the way, your calculator can do this in 10 seconds, and here's how.
But if you don't know how your calculator's doing it, you don't always know if it did it right.
That's true.
You have to be able to know what it's doing so you can understand it and interpret its results.